Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1817, finding the user's active minutes. This is a fascinating problem that challenges us to compute each user's unique active minutes and analyze the results. We'll break it down step by step and learn an efficient approach to solve it. Let's dive in. In this problem, we are given a 2D integer array called logs. Each entry in this array represents a user performing an action at a specific minute. For example, an entry, id_i, time_i, means that the user with id_i performed an action at minute time_i. A key detail here is that multiple users can perform actions at the same minute, and a single user can perform actions at different minutes. However, actions are only considered unique for a user if they occur at different minutes, even if the user performs the same action multiple times in a single minute. The goal is to compute the user active minutes, or UAM, for each user. UAM is simply the count of unique minutes in which a user performed actions. Once we have the UAM for all users, we need to construct a one-indexed array of size k. In this array, the value at position j represents the number of users whose UAM equals j. Finally, we return this constructed array as the output. To clarify the problem further, let's look at an example. Imagine we have the logs array as 0, 5, 1, 2, 0, 2, 0, 5, 1, 3, and k set to 5. Here's how the UAM is calculated for each user. User 0 performs actions at minutes 5, 2, and 5 again. Since actions at the same minute are not unique, the UAM for user 0 is 2 minutes, 2 and 5. User 1 performs actions at minutes 2 and 3, so their UAM is also 2. With these UAM values, we construct the answer array. For answer 1, there are no users with a UAM of 1, so answer 1 equals 0. For answer 2, 2 users, user 0 and user 1, have a UAM of 2, so answer 2 equals 2. The rest of the values in the array are 0 since no users have UAM values of 3, 4, or 5. This gives us the output 0, 2, 0, 0, 0. Now, let's consider another example. If the logs array is 1, 1, 2, 2, 2, 3, and k is 4, we calculate each user's UAM as follows. User 1 performs an action at minute 1, giving them a UAM of 1. User 2 performs actions at minutes 2 and 3, so their UAM is 2. Using these UAM values, we construct the answer array. For answer 1, there is one user with a UAM of 1, so answer 1 equals 1. Similarly, answer 2 is 1 because one user has a UAM of 2. For answer 3 and answer 4, there are no users with UAM values of 3 or 4, so both are 0. The final output is 1, 1, 0, 0. In a third example, consider the logs array 0, 1, 1, 1, 2, 1, 3, 1, with k equal to 4. In this case, all users, IDs 0, 1, 2, and 3, perform actions at exactly one unique minute. This means each user has a UAM of 1. When we construct the answer array, answer 1 will be 4 because there are 4 users with a UAM of 1. The rest of the entries in the array answer 2, answer 3, and answer 4 will all be 0 because no user has UAM values greater than 1. The resulting output is 4, 0, 0, 0. Finally, let's review the constraints and edge cases for this problem. The input size can be quite large, with up to 10,000 entries in the logs array. Each user ID can range from 0 to 10 to the power of 9, and the minute values can go up to 10 to the power of 5. The size of the output array, k, must be between 1 and the length of the logs array. Edge cases include scenarios where all users perform actions at the same minute, resulting in all UAM values being 1, or where all actions belong to a single user, leading to only one non-zero value in the answer array. It's also critical to ensure the solution efficiently handles large inputs and correctly counts users with the same UAM values. Additionally, if no user has a specific UAM value, the corresponding position in the answer array should correctly be set to 0. To solve the problem of finding the user's active minutes, or UAM, for each user, we need to break it down into two key tasks. First, we need to track the unique active minutes for each user by identifying distinct time values associated with their actions. Second, we need to count how many users fall into each UAM bucket based on their unique minute counts. Now, one obvious way to tackle this is by using a brute force approach, which involves using nested loops. The idea here is simple. For each user, we would collect all their active minutes, remove duplicates, and then count how many unique minutes they have. To implement this, we can create a dictionary that maps each user ID to a set of their unique active minutes. We then traverse through the logs to populate this dictionary. Once we have the unique minute sets for all users, we can compute the UAM for each user by simply checking the size of their set and tallying these counts in another dictionary. While straightforward, this approach has a downside. It involves redundant computations due to the nested loop structure, making it inefficient for large datasets. The brute force approach has a worst-case time complexity of n squared, primarily because deduplication for each user requires iterating over all their log entries. Although easy to implement, this inefficiency poses a challenge for large input sizes. To address this, we can use an optimized approach that leverages hash maps and sets for better performance. The intuition behind this method is to directly use sets to handle deduplication as we process the logs, eliminating the need for redundant operations. Specifically, we maintain a dictionary where each user ID maps to a set of their unique time values. As we traverse the logs, we add each log entry's time to the corresponding user set. Once all logs are processed, we calculate each user's UAM by taking the size of their set. Finally, we count the frequency of each UAM value using another dictionary. This approach is highly efficient because operations like adding to a set and updating dictionaries are O(1). In terms of complexity, it achieves O(n), making it well suited for handling larger datasets. However, it's important to carefully handle edge cases, such as users with no actions, to ensure correctness. Another way to solve the problem is by using a sorting-based approach. Here, the idea is to sort the logs by user ID first and then by time. Once sorted, we can deduplicate the logs in a single traversal by simply comparing consecutive entries. This eliminates the need for explicitly maintaining sets, as unique minutes can be identified directly during the traversal. The steps involve first sorting the logs, which ensures that all actions for a user are grouped together and in chronological order. Then, as we iterate through the sorted list, we count unique minutes for each user and simultaneously update the UAM frequency counts. While this approach is simpler in terms of storage since it doesn't require a hash map for grouping, it has a higher time complexity of O(n) log n due to the sorting step. For small to medium-sized inputs, it can be a viable option. However, for larger datasets, the sorting overhead makes it less efficient compared to the hash map and set-based solution. The optimized approach using hash maps and sets is the strategy we chose to solve this problem. It is the most efficient, with a time complexity of O(n), making it well suited for large-scale inputs. This solution is also straightforward to implement, as hash maps and sets naturally handle the operations required for grouping and deduplication. Moreover, it scales effectively and is robust enough to handle edge cases, such as users with no actions or multiple actions at the same timestamp. While the sorting-based approach is a valid alternative, its O(n) log n complexity makes it less competitive in terms of performance. On the other hand, the brute force method, though intuitive, is impractical for large datasets due to its inefficiency. The key insight that simplifies this problem is recognizing that sets automatically manage deduplication, allowing us to compute UAMs directly as the size of each user's set. Using a second dictionary to count UAM frequencies further avoids the need for nested loops, ensuring optimal performance. By striking a balance between time efficiency and implementation simplicity, the hash map and set-based solution provides the best overall approach for this problem. In this problem, we are tasked with determining the user's active minutes, or UAM, based on a list of activity logs. Each log entry contains a user ID and a timestamp, and our goal is to calculate how many unique active minutes each user has, then count how many users fall into each UAM category. To solve this, we'll follow two primary steps. First, identify and count the unique timestamps for each user, and second, aggregate the results to compute the number of users for each distinct UAM value. We begin by parsing the input logs. The input is a list where each entry represents a user ID and a timestamp. To track this information, we use a dictionary where the keys are user IDs, and the values are sets of unique timestamps. Sets are particularly useful here because they automatically eliminate duplicate timestamps for the same user. For instance, if the input logs are 1, 10, 2, 20, 2, 20, 2, 30, 1, 10, 1, 15, after processing, the dictionary would look like this: 1, 10, 15, 2, 20, 30. This structure ensures efficient grouping and deduplication of timestamps for each user. Once we have grouped the timestamps by user, the next step is to calculate the unique active minutes for each user. This can be done by finding the size of the timestamp set for each user in the dictionary. For example, if user_to_times equals 1, 10, 15, 2, 20, 30, the unique active minutes for user 1 are 2, and for user 2, they are also 2. This gives us a new dictionary, user_um equals 1, 2, 2, 2, where the key is the user ID and the value is the count of unique active minutes. After that, we proceed to count how many users have each unique UAM value. For this, we use another dictionary called UM_count, which maps each UAM value to the number of users who have that UAM. Iterating through the user_um dictionary, we increment the count for each UAM value in UM_count. For instance, given user_um equals 1, 2, 2, 2, the resulting UM_count dictionary would be 2, 2, indicating that 2 users have exactly 2 unique active minutes. With the UAM counts calculated, we can now format the final output. The output is an array where each index corresponds to a UAM value, and the value at that index represents the number of users with that UAM. To build this array, we use the UM_count dictionary and handle sparse UAM values by filling in missing entries with zeros. For example, if UM_count equals 2, 2, the output array would be 0, 2. Here, the value at index 0 corresponds to UAM 1, which has no users, and the value at index 1 corresponds to UAM 2, which has 2 users. This transformation ensures the output is formatted correctly for all possible scenarios, even when some UAM values are absent in the input logs. The use of dictionaries and arrays in this step allows us to efficiently compute the result while handling edge cases seamlessly. Several key insights make this algorithm both effective and efficient. First, using sets to track timestamps ensures that duplicates are removed automatically, simplifying the implementation. Second, dictionaries allow for constant time insert and lookup operations on average, making them ideal for tasks like grouping timestamps and counting UAM values. Third, directly constructing the result array from the UM_count dictionary avoids unnecessary computations, especially for sparse UAM values. Finally, it's important to consider edge cases. These include logs with duplicate timestamps for the same user, users with only one log entry, and scenarios where no users exist for certain UAM values. Additionally, the algorithm handles empty input logs gracefully by returning an empty result array. The combination of efficient data structures and careful handling of edge cases ensures the algorithm is robust across all inputs. Let's analyze the algorithm's complexity. For time complexity, parsing the logs requires O(n), where n is the number of log entries, as we iterate through the entire input once. Counting the UAM values involves O(u), where u is the number of unique users, since we process each user in the user_to_times dictionary. Constructing the result array takes O(k), where k is the maximum UAM value. Combining these, the total time complexity is O(n plus u plus k). For space complexity, the dictionary user_to_times requires O(n) to store all unique user timestamp pairs, while the result array needs O(k) space. Thus, the total space complexity is O(n plus k). Optimizations like directly building the result array from the UM_count dictionary and using sets for timestamps ensure minimal overhead and maximum efficiency, even for large input sizes. The solution involves finding the unique active minutes, UAM, for each user and counting the frequency of those UAM values. We first initialize a default dict where each user ID maps to a set of timestamps. This set ensures that only unique timestamps are stored for each user. Next, we iterate over the logs and populate this dictionary with user activity data. After gathering the unique timestamps for all users, we calculate the UAM for each user by determining the size of their corresponding set of timestamps. We then update a list UM_count of size k, where the index represents the UAM value, adjusted by -1, and the value at that index represents how many users had that specific UAM. Finally, the UM_count list is returned, representing the count of users for each UAM value from 1 to k. This implementation is efficient and handles edge cases, such as duplicate entries and users with no activity, by leveraging sets to ensure uniqueness and by directly mapping UAM values to indices in the result list. Here, we begin by importing the necessary libraries, including java.util**, which provides us with the data structures we need for this implementation. The main method, finding users' active minutes, takes two inputs, a 2D array logs and an integer k. The logs array contains pairs of user IDs and timestamps, while k represents the maximum number of unique active minutes we want to count. In step 1, we create a map called user activity where each key is a user ID, and the value is a set of unique timestamps. This ensures that we only track distinct timestamps for each user. We populate this map by iterating through the logs array. For each log entry, we extract the user ID and timestamp, initialize a new set for the user if they aren't already in the map, and then add the timestamp to their set. This gives us an efficient way to track unique timestamps for each user, which is the foundation for calculating their unique active minutes. After constructing the user activity map, we move to step 2, where we calculate the unique active minutes for each user. To do this, we initialize an array UMCount of size k, where each index represents the number of users with a corresponding unique active minute count. For example, UMCount 0 tracks users with 1 unique active minute, UMCount 1 tracks users with 2 unique active minutes, and so on. We iterate over the sets of unique timestamps stored in user activity. By calling the size method on each set, we determine the number of unique active minutes for that user. If this value, UM, is less than or equal to k, we increment the corresponding index in the UMCount array. Finally, the method returns the UMCount array, which provides the desired distribution of users across the different unique active minute counts. To solve this problem, we start with the first example input. Here, we are given logs that describe user activity, where each entry contains a user ID and a timestamp. Our goal is to calculate the user active minutes, or UAM, for each user and then count how many users fall into each possible UAM bucket from 1 to k. First, we initialize two data structures, a default dictive sets called user_activity, which helps us track unique timestamps for each user, and a list called UM_count, initialized with zeros, with a length equal to k. This list will store the count of users in each UAM bucket. Next, as we iterate through the logs, we process each log entry. For the first log, user 0 performs an action at timestamp 5, so we add 5 to the set associated with user 0 in user_activity. Then, for the second log, user 1 performs an action at timestamp 2, and we update user_activity to reflect this. For the third log, user 0 performs another action at timestamp 2, so their set now contains both 2 and 5. Importantly, when we encounter duplicate logs, such as 0, 5, again, the set ensures there's no change to user_activity. Finally, processing the last log adds timestamp 3 to user 1's set. At this point, user_activity is fully populated, showing unique timestamps for each user. Now that we have the user_activity dictionary, we calculate the user active minutes for each user. User 0 has 2 unique timestamps, so we increment the corresponding index in the UM_count list. Since UAM values are 1-based, we increment the bucket at index 1, which represents 2 active minutes. Similarly, user 1 also has 2 unique timestamps, so we increment the same index again. This results in UM_count being updated to 0, 2, 0, 0, 0, meaning there are 2 users with exactly 2 active minutes. Finally, since we've processed all users, we return the UM_count list as the result, which is 0, 2, 0, 0, 0. This represents the count of users for each UAM bucket, where the first bucket corresponds to 1 active minute, the second to 2 active minutes, and so on. In the second example, we explore an edge case where all logs belong to a single user, and all timestamps are identical. Here, we initialize user_activity as an empty dictionary and UM_count as a list of zeros with a length of 3, as k is 3. When processing the logs, we see that user 2 performs the same action at timestamp 3 multiple times. However, since we're using a set to store timestamps, duplicate entries are ignored, and user_activity ends up with a single entry, 2, 3. After processing, we calculate the UAM for user 2. With only one unique timestamp, we increment the first index of UM_count, corresponding to 1 active minute. This updates UM_count to 100, indicating that there is one user with exactly 1 active minute. Finally, we return 100 as the result. In the final example, we handle a case where there are no logs at all. Here, we initialize user_activity as an empty dictionary and UM_count as a list of zeros, with a length of 3 since k is 3. Since there are no logs to process, user_activity remains empty. Because no users are active, there are no UAM values to calculate. As a result, UM_count stays 0, 0, 0, indicating that no users fall into any UAM bucket. The final output is 0, 0, 0, which we return as the result. This example highlights how the algorithm handles scenarios with no user activity seamlessly. To analyze the time complexity of our solution, we break it down into steps. First, we focus on building the user_activity dictionary. This involves iterating through the logs list, which contains n entries, each represented as a pair of user ID and timestamp. For each entry, we add the timestamp to a set associated with the corresponding user ID in the dictionary. On average, inserting into a set is an O(1) operation due to efficient hashing, but in the rare worst-case scenario, hash collisions could cause this operation to degrade to O log m, where m is the current size of the set. As a result, the time complexity for this step is O(n) in the average case and O(n) log m in the worst case. Next, we iterate over the user_activity dictionary. This dictionary contains unique users, and for each user, we calculate the size of their set of timestamps, which is an O(1) operation. Thus, iterating through the user_activity dictionary has a time complexity of OU. Now, we consider the step where we update the UM_count list. For each user, we determine their unique active minutes, or UAM, and use this value to update the corresponding index in the UM_count list. Since this update operation is O(1) per user and there are U users, the time complexity for this step is OU. When we combine all these steps, the overall time complexity of the solution in the average case is O(n plus U). However, in the rare worst case where hashing and set operations degrade, the time complexity becomes O(n log m plus U). This worst-case scenario is uncommon in practice but is important to consider. Shifting focus to space complexity, the first contributor is the user_activity dictionary. This dictionary stores a set of timestamps for each user. If there are unique users and n total log entries, and assuming most timestamps are unique, the dictionary consumes O(n) space. Additionally, the UM_count list contributes to the space complexity. This list has a fixed size of k, where k represents the maximum possible number of unique active minutes. Since k is constant relative to the input size, the space complexity for this list is OK. Another component of space usage is the input itself, specifically the logs array. This input contains n entries, so it occupies O(n) space. However, because the input is part of the problem definition and not part of the algorithm's auxiliary space, it doesn't count toward auxiliary space complexity. Combining these factors, the auxiliary space complexity of the solution is O(n plus k, while the total space complexity, including the input, is O(n). When compared to a brute force approach, which would involve iterating over all user timestamp pairs and explicitly counting unique timestamps for each user, our optimized solution is far more efficient. The brute force method has a time complexity of O(n squared in the worst case, while the optimized approach leverages hash-based data structures to achieve O(n plus U). To summarize, the optimized solution has an average case time complexity of O(n plus U, and a worst case time complexity of O(n log m plus U). Its auxiliary space complexity is O(n plus k, with a total space complexity of O(n, when including the input. By efficiently using hash-based data structures like dictionaries and sets, the optimized approach avoids redundant computations and outperforms the brute force method, especially for larger inputs. This makes it a robust and scalable solution for the problem of finding users' active minutes. When solving this problem, there are a few common mistakes to watch out for. First, not handling duplicate times correctly for each user is a frequent issue. If you simply count every time_I value for a user without checking if they're unique, you'll end up with incorrect results. This is because the problem explicitly asks for unique active minutes, and duplicates shouldn't be included. To avoid this, use a set, which automatically ensures uniqueness. Another mistake is failing to initialize the UAM buckets correctly. For example, if you create an array of size k based on the maximum possible unique active minutes, but don't account for users with fewer UAMs, you might encounter indexing errors. Lastly, inefficient data structures can also be problematic. For instance, using a list to track time_I values and then deduplicating them manually is unnecessary and adds extra time complexity. A set is a more efficient choice for this task, as it handles duplicates directly. Another challenge arises from incorrectly handling edge cases. For instance, you might overlook scenarios where multiple users have 0 unique active minutes or where all users have the same number of UAMs. Ignoring these edge cases can lead to errors, especially if your implementation assumes every user has at least one unique active minute. It's also important to consider input constraints. Overcomplicating the solution for small inputs, such as iterating unnecessarily when the number of logs n is only up to 10,000, can result in inefficiencies. A good solution should work optimally within the given constraints and avoid redundant computations. These considerations are key to building a robust and efficient implementation. From an interview perspective, this problem is a great opportunity to demonstrate several important skills. First, it tests your ability to recognize patterns in data aggregation and processing. Using a dictionary or hash map to group data by user IDs is a fundamental technique in problems involving grouping or counting. Additionally, the use of sets for deduplication is an important skill to highlight. Interviewers are often looking for candidates who can select the right data structure for the task, and sets are ideal for ensuring uniqueness efficiently. Don't forget to discuss edge cases explicitly, such as handling empty logs, multiple users with no UAMs, or large input sizes. Finally, emphasize optimization. For example, reducing time complexity to O(n) by using hash maps and sets, rather than relying on nested loops or manual deduplication, shows that you can write scalable code. If you're looking for related problems to practice, several LeetCode questions share similar concepts. For example, LeetCode 347, top k frequent elements, involves aggregating data into buckets based on frequency. Similarly, LeetCode 692, top k frequent words, requires counting occurrences and handling ties, which often involves sorting. LeetCode 49, group anagrams, focuses on grouping data efficiently using a hash map, while LeetCode 451, sort characters by frequency, deals with counting frequencies and sorting the results. These problems reinforce the same fundamental skills of grouping, counting, and optimizing for efficiency, making them excellent practice for sharpening your understanding of this problem's core concepts. There are multiple approaches to solving this problem, each with its own trade-offs. A brute force approach involves iterating through the logs, manually counting unique times for each user, and then calculating the UAM buckets. While simple to implement, this method is inefficient for large inputs due to its O(n)² complexity. A more optimized approach uses hash maps and sets. Here, you group time_I values for each user in a hash map, ensuring uniqueness with a set. Then, you count the size of each set and populate the result array. This approach is efficient with O(n) complexity but requires careful handling of edge cases. Finally, a sorting-based approach involves sorting the logs by user IDs and iterating through them to count unique time_I values for each user. While this method avoids using a hash map, it increases time complexity to O(n) log n due to the sorting step. Each approach has its strengths and weaknesses, so choose the one that best fits the problem constraints and context. Great job! In this session, we solved LeetCode problem number 1817, finding the user's active minutes. We learned how to use a hash map to group and count user activities, analyzed the solution's complexity, and highlighted key takeaways. Remember to practice similar problems to strengthen your algorithmic skills. Thanks again for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!